Hey everyone, so we're going to talk about vector projections. We had just talked about dot product, so let's see what this is about. We're going to consider a force applied to an object moving along a path. So we have an object, let's say sitting on a path, like on the ground maybe, and a force is applied. In my drawing, the force is like pulling upward sort of at an angle, and it's being applied to this object, and it's moving that object in a certain direction. So this vector here is representing the direction that my object is being moved. Okay? So the idea of a vector projection comes from this force vector that's being applied to the object in moving it. So let me put some letters on here. I'm going to call this force vector U, and I'm going to call this direction vector V. And so what we end up with here is this idea of a projection vector is this right here. So we have this vector, and it's from the projection of U onto V, and we call it the projection of U onto V. Okay, and this is a resulting vector. You can kind of think of this like a shadow, almost like a, let's see, my sun will be red, and I have like the light shining up here from the sun and shining down on my force vector, and it's creating this shadow, which is the projection vector. Alright, so what is our formula for this? So the vector projection of U onto V is what we're interested in. So vector projection of U onto V is the following, and I'm going to give you actually 4 different versions of the formula, and then you just use whichever one depending on the situation you have, and that means like what kind of information you're given in a particular problem. So the projection of U onto V equals, here's our first version, U dot V divided by the magnitude of V, and that's going to be times the V over the magnitude of V. Alright, now these are all technically vectors, if I put my vector symbol on all of them. Alright, so this is my first version. Now, this one I want to point something out to you because we've seen this in the past. The way that this is written, if you recognize this, this is the unit vector in the direction of V. So this just represents the direction. Okay, so when you take a vector and you divide it by its own magnitude, it's giving you the direction. So it's giving you a unit vector in that direction. And then any vector can be written as a product of its length and direction. So that means that this part is actually the length or magnitude in this direction. So this is the length of our projection vector. So this is a pretty meaningful way to write our projection vector. But let me give you the other versions as well. Okay, so that's one version. Then we have that this is also equal to U dot V over the magnitude of V squared times V. Okay, this version is just if you want to take this other magnitude out here and kind of bring it in. Third one, you can say U dot V over, well, we talked about this with dot products, when you have the magnitude of a vector squared, it's actually that vector dotted with itself. So V dot V, and then times this vector V in the back. Okay. One more version, and this last one is also going to be a fairly meaningful version. Let me go ahead and erase my beautiful drawing of the sun and my projection vector. Okay, and so then we have, let me just put our notation back on, projection of U onto V is the magnitude of U times cosine of the angle theta times V over the magnitude of V. Okay, so this one here, let's see, this again represents the direction, And so this represents the length. Okay, so remember with the dot product we talked about theta being the angle between the two vectors. So this theta was the angle between u and v in my drawing. That was theta. Now, this part I'm going to point out because we have a different name for that part altogether. It's called the scalar component. So we have the following. Scalar component, and so the notation is SCAL, or scalar, it's the shortened version for it, of u onto v equals this part right here, magnitude of u times cosine of theta. And you can kind of think of this like the length of the shadow. And so it's this part here, but just this length. Okay, so that's magnitude of u cosine theta. Alright, so let me draw you two versions of this though, because sometimes you are going to have your vector projection on the negative of the direction. Let me explain with a drawing. So go ahead and erase my formula right there. So two versions of this now. We have this situation right here, but let me draw it a little bit better. And then I'll draw the next one. So u and v, and then over here, this is the other one I was mentioning. Let's say u points this way, but v still points that way. Okay, so theta is this angle in between. This is still theta. Okay, so in this case, right here, this length, the length of this projection vector is magnitude of u cosine theta. Exactly what we said up here. But in this one, it's a little different because you have to take v and kind of consider the negative of v over here. And so when you do this projection, it's actually going to come down onto here. Okay, and then this length, you're going to actually represent that as negative u, magnitude of u cosine theta. Alright, so just a small difference if theta is more than 90 degrees. Okay, so let me add one more piece to the scalar component of your projection. Another way you can write that is u dot v over the magnitude of v. So just another version for you. Basically the length part of your projection vector. Okay, that was from this version. This was from the very first version of the formula that we wrote down. Alright, let's go ahead now. We're ready to take a look at an example. So we'll say if the vector u is 4, 1, and the vector v is 3, 4, we're going to find the projection of u onto v. So find projection vector of u onto v. Now this is nice two-dimensional vectors, so I'm actually going to go ahead and just draw this for you, so then if you're a visual learner, you can kind of make sense of all this. So let's draw this out in 2 dimensions. So I have the vector that ends at point 4, 1. So let's draw my tick marks here. 4, 1, 2, 3, 4, 5. Okay. So 4, 1 is right there. So my vector starts at the origin and ends at 4, 1. That's u. Okay. Let's go ahead and draw v. It terminates at 3, 4, starting at the origin and stopping here. That's v. The question is, what is the projection of u onto v? So the way you draw this is you kind of have to think about your light, or like my sun drawing or a flashlight shining up from here. Okay, so from u onto v, casting its shadow that way. And so what we have here is you shine down like at a 90-degree angle there. So my drawing might be a little off, but something like that. Okay, and so the projection vector would be right here. Okay, so that's what it should look like. And so let's see what it is if we work it out algebraically using our formula. Alright, so let's get rid of this and our scalar component there, and that one too. And so we have 4 different versions of our formula. We only have the components of the 2 vectors, so it wouldn't be very useful for me to use the version of our formula that used the angle. I mean, I can do some work and find the angle, but let's not use that one just because there's other versions of this formula that I can use faster. So the projection of u onto v, I'm going to go ahead and use the version u dot v over the magnitude of v times v over the magnitude of v. Okay, that unit vector in the direction of v, and then this result here. So what I'm going to do is I'm going to start doing some side work where I just find all these things that I need. So let's go ahead and start with the magnitude of v. So the magnitude of v is just going to be the components of v squared, added, and then inside the square root. So that's going to be square root of 9 plus 16, which is square root of 25. So that's just 5. Okay, that's going to go in my formula. Now also, I'm going to find the dot product. So as a reminder, the dot product, you just take the components of the vectors and you start multiplying them component-wise and then add those up. So I'm going to multiply the 2x components, so it's going to be 4 times 3, and then I'm going to multiply the 2y components, so 1 times 4, and then I always add those. So this is going to be 12 plus 4, so this is 16. Alright, so I have everything I need for my formula. So the projection of u onto v is going to be, let's see, u dot v was 16, the magnitude of v was 5, and then the magnitude of v was 5, again in the back, and then v, this is actually still the vector v. So this is square angle bracket 3, comma 4, close angle bracket. So let me just make that very clear. This one here was the only one that remained a vector. This became a magnitude, which is a number. This is a number. This was a number. But that stayed a vector. And so we'll just make this look a little better. And hopefully it makes sense that it should stay a vector because it was a projection vector. This vector projected onto the other one to form a new vector. So over here we're going to get 16 25ths times 3 comma 4, and then remember when you're multiplying by a scalar times a vector, you can just distribute that scalar inside the vector and you'll get the result. So now I'm ready to get rid of that. This is going to be 48 25ths comma 64 25ths, and if you use a calculator, if you want to actually divide that out, let's see, I got 1.92 comma 2.56. And let's see visually, I know my drawing might be off a little bit, but let's see if it kind of lined up and made sense. 1.92, so 1.92, okay, that's like about right there. 2.56 is like right there. Oh, okay, pretty close. My drawing's a little off, but that vector definitely ends somewhere right there. So solved it visually, solved it algebraically. That's the projection of one vector onto another one. Alright, the very last thing we're going to do in this section is consider something called work. Alright, so the idea of work. This is work done to an object. Specifically, it's going to be in moving it. So here's my object. I moved it from here to here, and I'm going to talk about the work done or required to do that. So the work done by a constant force, we're calling that F, that vector, that's the force on the object, in moving an object through a displacement D. So how far I'm moving it is D. The force applied to move it is F. Okay? So I'm going to put a point here. That's my starting point. I'm going to call that P. And over here, that's going to be my ending point. I'll call that Q. So from P to Q, that displacement is actually this vector here. So D, the displacement, is actually the vector PQ. Okay, so you could call it the vector D, or just say D equals the vector PQ. Now the force that's applied here, let's go ahead and draw it in purple, is right here. So I have my force vector F. And so what we have actually is projection, a projection vector that we're interested in. And so I'm going to kind of extend my drawing out with this projection vector. Let's go green. Okay, so if I kind of extend PQ so that I have something to project onto, my projection vector right here, let's see, my shadow coming down, is this result. Okay, so then there's an angle formed between this vector that I projected onto. So technically, if you want to think about it, you can take this force vector and kind of put it right back here at the starting point and think of that as the angle. I'm just dealing with the angle over here. So there's our angle theta. And so this length we've already talked about. This length right here is the magnitude of F times cosine of theta. In the previous formula for the scalar component of the projection, I used U because U was the name of my vector. This is just my vector F, so it's the magnitude of this vector times cosine theta. And if you forget this, you can always use trigonometry to solve for this length, okay? Thinking of this as a right triangle. All right, so then let's put this together. And so the work is equal to the following. So work is the scalar component of the projection vector. So the scalar component of F on to D, okay, this part here, scalar component of F onto D, times, let's see, I'll kind of move down here, so times the length of D, Okay, so let's make that look a little better. We don't want to leave our formula like that with words. Let's figure that out. So then that becomes, the scalar component is magnitude of F times cosine theta. And then the length of D, well, that's just the magnitude of D. So that's the magnitude of D. Okay, well, does that look like anything we've seen before? You might say no, but the answer is technically yes. If you don't remember, it was just previously when we were learning about the different formulas for dot product. Let me erase this and remind you. So one of your versions of your dot product formula had this in it. And so what we have, if I rearrange it just so it's more meaningful, this might look more familiar. If I say magnitude of F times magnitude of D times cosine theta, maybe that looks a little more familiar. I think when I showed you I used U and V. So this is just equal to F dot D. And that's your formula for work. Okay? So it's just a dot product of the force dotted with the displacement. So that's how you calculate work. So let's just do a really nice quick example with some numbers so you can put this all together. And so let's say we want to know how much work. How much work does it take to slide a box 30 meters along a path by pulling on it with a 210 Newton force. And this is going to be at an angle, let's erase this, of 31 degrees. And this is from a horizontal. You can assume it's from a horizontal if it doesn't say, but I'll just make sure you know it's from a horizontal. Alright, so it might seem like there's a lot in this problem, but really it's super straightforward because we actually know all the values we need to go right into our formula. How much work does it take to slide a box? We're sliding it 30 meters, that's our distance or displacement, along a path and we're pulling on it with a force of 210 newtons, and we know the angle that our force vector forms with the horizontal, which is basically the path as well that this object's on. So you can draw a picture if you want. It's basically the same picture I was drawing just a minute ago. We're moving this vector, there's a force being applied at a 31 degree angle, and you're moving in a horizontal, or you're moving in a certain direction. Same picture we already saw, but the idea is you basically just need these numbers. So the work, you could say W, or you can write out work, equals, let's see, well, the magnitude of the force is right here, okay? So the magnitude of the force, let's just label that, this is F, magnitude. So that's 210, okay? And then, let's see, times the magnitude of the displacement, well, that's how far we're moving it, so that's actually right here, 30 meters, so times 30, and then cosine of the angle between the vectors, which is 31 degrees. That's it. That's the answer. I want to definitely make it a little more meaningful, maybe with the calculator, but that's it. And so with the calculator, you're going to get 5,400 roughly. Let me say about. Okay, so about 5,400. And then it would be Newton meters, which is joules. So you can say Newton meters or joules on that one. Okay, so that's it for this one.